Hello. Good afternoon, all. Am I audible?
Hello, hello.
Yeah, am I audible?
Yes, sir, you are audible.
Okay. So in this session, we are going to discuss about the transformers. So how many of you have clear idea about transformers?
Realize मेरा mic off है.
Hello? Are you?
अच्छा लाइक बोल दिया. I didn't realize कि मेरा mic off है.
Am I audible to the participants? Hello? Okay,
Hello. Yes, sir, you are audible now.
fine. So how many of you have clear idea about transformers and attention? And then we will discuss about the practical implementation also. So how we can implement transformers. Okay. So shall we start with transformers, attention, and then go for coding? Is that fine? Can anyone respond in the chat? Okay. Okay. Fine. So first, I will share the screen. First, we will discuss about why we need attention and what actually the transformer. Okay. And then we'll look into the code. Okay. So let me share the screen. So here first we discuss about, I will show one video, okay? So that will help you to understand better. Okay. J. Elmer transformer, the illustrated transformer, okay? So this will help you to understand the transformer. So, okay. So the chat GPT, everything, the latest LLMs are based upon the transformer architecture, okay? So let's see, initially, this is a transformer at higher level. So what a transformer can do is, it can take an input, okay? So let this be a black box, and it can do the translation or image caption, whatever it may be. So it can take some text and it can give the output in some language, okay? Next. So if you go next step inside into the transformer, so transformer is a combination of encoders and decoders. So wherever you have seen such type of architectures, encoders and decoders, only first time in transformer or earlier also you got this kind of architectures? Can anyone tell me? So my question is this encoder decoder. So transformer is the combination of encoder and decoder. This is the first time, means the transformer is having this architecture, or other networks are also having same architecture. Very good, Suman Paul. So LSTM and RNN and encoder decoder, auto encoders also. Okay, fine. So next, we'll go one step deeper. So encoder block is a combination of encoders, collection of encoders, and decoder is block is also collection of decoders. So encoder will feed in the data. It will go through some encoding, some mathematical operation. See, either whatever you call, it's a mathematical operation. And then that the output from the Last layer is what we are going to pass it to each layer, and then decoder will start. Next, encoder. Encoder is a combination of self-attention and a feed-forward neural network. So each encoder contains two things. One is the self-attention block, and second one is the feed-forward neural network. Okay. Next, see here. So self-attention, feed-forward. Next, like this, all multiple blocks. Decoder, see, self-attention. Next, encoder, decoder, attention, feed-forward. So feed-forward is common. Okay, attention mechanism. So both decoders and encoders are a combination of self-attention networks, feed-forward networks. Okay, so now you see, if you give any input, it goes through self-attention. Attention will give you the output, and that output goes to feed-forward network, and that is the output from the encoder. That will go to the another block, another encoder block, another encoder block. Okay, so this is what happens here. So each word which we are embedding, and that embedding goes to self-attention. Self-attention will give you an output, and that output we are giving it to feed-forward network, and it gives the output. That will go to the another. So output of one encoder forms an input to the another encoder block. Like that, it will go through multiple encoder blocks, and the final encoded operation, the output is what we are giving it to feed to decoder, and decoder is also performs the same set of operations, some set of operations. Okay, so what actually the attention is? Can tell me what actually the attention? Can anyone tell me why we need attention, and what actually in a layman terms, if you want me to explain in a layman term, what actually an attention? Anyone? Hmm. Feature selection, the importance associated. Okay, summary, let the current context to weight the importance to give importance. Okay, fine. Okay, so let me out of this to weight the importance of different token. Summary related to the importance associated with features. Okay, so let me show you. One second. Okay, so I got the PPT. Let me share that. See what actually attention means. Yes, yes. Let me show you that. Okay. So if you see here, what is meant by attention? Attention means Let me open this. Okay. So first 1 hour we'll try to understand 20 minutes. We'll try to understand what actually the transformer attention, and then we can implement the code. Yes, Pooja Soni. Notebook I have shared. So notebook is more important. PPT somehow I missed. So okay. So this time I will share here itself. So everyone in the meeting. So this is the okay. So now itself I will share. Okay. So this is what we are going to discuss. So I already shared to everyone. Okay. And that notebook. Okay. So that notebook I will check. I will share. Okay. So today's mm, so transformer triple DM is what we're going to discuss. So if you see here, what actually the transformer? Okay, so I will directly come to the important part. Okay, so this is the vision transformer. So what this vision transformer will do is it will break the image into patches. So this is a full image. This full image is made into small patch, small subset, and it will work on these patches. Okay, now see what will happen. Suppose, assume that we have a car. Please read this. So we have a car in an image. Now, as we are breaking the image into small patches, okay, how to understand what actually this image is representing, because it is a small patch. Now, let's see what will happen is similarly in this car, what happens? There is a small patch here. Understand a small patch, like a few pixels of a wheel, doesn't give you much information on its own. So you cannot understand if I just take this black part, and what you will observe, it will be a small black patch. So it won't give you the context, full context. The patch may be a part of the car, or maybe a bicycle, or just a random black color. Okay. So okay. So this is the patch. Now, to make sense of a patch, what we need to do is it has to look, okay, it needs to look at other patches in the image, like the car body or bicycle frame. So you have to check. So this small patch, okay, so where I'm putting in, to whom I need to join so that I can get the context. The context, see here, to make sense of that patch, meaning of the patch, deeper understanding this particular part of the subset of the image, it needs to look at other patches in the image, all other patches. So when I'm here, suppose the same patch is here, so it has to look into other patches, this patch, okay, this patch, all other patches. Image is assumed to be a set of patches. So you have to look into other patches, then you will come to know who you are. Okay, see here, the context provided by the neighboring patches helps it understand what the wheel belongs to. Got it? So now see here, by looking at all patches, so not only the nearby patches, you look into all other patches of the image. Okay, the model can capture global information about the entire image. So it helps it understand the relationship between far apart patches, which is useful because important parts of the image might not always be next to each other. So what it has to do, the model has to learn is this patch is related or nearer to which part of the image. So every patch it will take. So we are assuming, see, this is the patch of the images. So how the vision transformer will work? We are breaking the image into multiple patches. And for each patch, we will look into all other patches of the image. See here, by looking at all patches, not just by near ones, the model can capture global information about that particular patch. So this particular patch, okay. So you understand how the model is learning here, okay. So okay. So what the transformer is working is, okay, so it is working on the property. What it will do, it will break the patches, the images into patches. So that is what the problem, the functionality, and it is advantageous. Okay, so somewhere we have seen the vision transformer. Okay, so vision transformer works with patches. Okay, like this. So each image, any input, if we want to develop a thorough understanding of the image, we are not focusing on the entire image. We are just dividing into patches. For each patch, I want to understand the context. What I will do, this patch, how it is related to this patch. This patch, how it is related to this patch. So for all other patches of the images, okay, so this is the patch. That means this one. So here I have a patch. If you just take this patch, that means this small, this black color like this, and if we try to understand what actually this black will convey, see, it is not conveying anything. No one will say that it is a part of a black chair or part of a car. No one will say. See, it is just like a, now I can see, I just taken the patch from the car tire. So I can also create same patch. See, okay, that's it. Now, no one can differentiate. But this is from the car, this is a normal paint. So in order to get an idea of who am I, who is this, that means if this color, this patch is thinking, who am I? Okay. So to know that, it has to look into all other patches. So it will check what about this patch, how much similar this patch to me. Okay. Like this, all of, like this patch also. Okay. Like this patch also. So it will try to each part of the image, each subset of the image, finding to whom I am nearer is called as attention. So this patch, for which I need this patch, because if I take it out, we cannot understand the context of the tire. So it has to look into the all other patches, and those belongs to the tire. Those belongs to the same class will have higher attention. So if I want to know who am I need to give more importance to this. I need to give more importance to this. Okay. I need to give more importance to this. Okay. I need to give more importance to this because this part is here. So I can give, suppose if I give 100 to importance to this guy, I can give 95 importance to this. And we have taken this from this part, so I can give only say 10%. So this is how every part, every patch tries to understand where I fit into the whole part of the image. So in this, like this, what is happening? We are computing the attention to each and every patch. So one patch to each and every patch, we are computing the dependency. Am I belonging to the same context? Am I belonging to the same context where this patch is present or the patch is conveying to how much it is mapping? So that is what my attention score. So what is happening? I am focusing on entire image. So all image patches is what we are checking here, and I am computing the dependency where I can fit in better. If I take this, if I take this, if I take this, I can frame myself. I can understand where I belongs to. With this information, I cannot understand who am I. For those who helps me to understand where I fit in my context, who am I, that is called the attention mechanisms. Okay. So like this. Where is that car? Okay. So this helps it understand the relationship between far apart patches also. Far apart patches also, I can understand the relationship, which is useful because important parts of the image might not always be next to each other. Okay. So that is what. Okay. So why not just look at one patch? If each patch looked only at itself, okay, or its immediate neighbors, it would miss the big picture. So if you are only looking at patch that shows a car wheel, you won't be able to tell that it's part of the car unless you look at another patches. So you have to understand the context. Two things. What he's telling, if, see, why I have to consider the entire car? Why not you are considering only the patches of nearby? Okay, so nearby patches, I will consider, I will take these patches. Okay, so again, I will come to know that, okay, this main patch, the source patch, this patch, this patch, it belongs to these back patches. We will come to know that it is a tire, but that is not sufficient. So if you want to thoroughly understand this entire image, we have to know that this is the tire, this is the patch which is part of this tire, and this tire is part of the car. So that is what we have to understand. Context. So if you look into this small patch, you are not going to get the context. To understand what this image is, I need to understand its neighbors. Not only the neighbors, you have to understand this entire part is subset of what is the global context. Then only you clearly say that I am a patch of a tire of a car. So complete information you are going to get. So that is how we are learning about each word, each part of the image. So you assume that now this is I'm talking about the patch of the image. Similarly, the sentence also. So we are doing the image to image translation, right? So I will have some set of words which I can use it to translate. So I need to understand the context of the each word. To understand the context of the each word, I need to understand how much I'm related to this. That means how much importance I need to give to this word to understand me better. How much importance I need to give to this word to understand me better. So same here. So this analysis to understand the context for to the all parts, all patches, or all the words of the input is called as attention. Where I need to pay my attention to understand me better. So you have this guy has to focus on this, this, then this, least is this one. Because, okay, so nearby, first I need to understand the car, then I need to understand tire, and then I need to understand the car context. Okay, so if you see here, okay, So in an image, understanding a small patch, like a few pictures of wheel, doesn't give you much information on its own. So if you just try to understand about this, you won't understand. Just try to understand a single word within a sentence, it won't give you much information. To understand the meaning, the role of each word, you must learn at least 2 to 3 words before and after. Then only the context of this word can be learned better. The patch may be part of a car or a bicycle or just a random circular shape. To make sense of a patch, what it is, it needs to look at other patches in the image to understand bigger picture. So the context provided by the neighboring patches helps it understand what the wheel belongs to. Yes, this is a patch and I belongs to a wheel and the wheel is part of the car. So that is what the complete picture I need to understand. This is a word and in which meaning I use this word. To understand that, I need to understand other words also. So which word will help me? May not be a nearest word, but sometimes a farthest word may help me. So that is called as attention. So with whom I need to check? Which part will help me to understand better? In the entire car, who am I? So with whom I need to cross check so that to understand who am I? What is the context of this word? In which context the word has been used? To know that, I need to look into various words of the sentence. Which word I need to focus more? So that how much importance I need to give is what we are computing the attention mechanism. By looking at all patches, the model can capture global information about the entire image. This helps understand the relationship between far apart patches. What the relationship between this patch and this patch and this patch, which is useful because the important parts of the image might not always be next to each other. To understand the context better, maybe far ahead patch may be helpful. May not be in this car case, but in general, in sentences, okay. So see, some examples in the YouTube I just studied. So Dawal. So Dawal likes something, something, something. So sorry, suppose Dawal likes samosa and idli. And then after that, some set of lines, then says that which confirms double cuisine is dash. So if I want to fill this word, what is the double cuisine? So if I want to fill this word, the information, the correct answer may not be given by this, may not be given by this, may not be given by this. So all other words in these three sentences may not helpful. But which are the words are helpful? Dhaval likes the samosa and idli. So these two words which spread far ahead than the required answer. So here is what I need to fill the answer. Here is required. To fill this, these are not helpful. Only these two are helpful. So the patching context, I'm checking the context. See here, to understand the relationship between far apart patches, which is useful because important parts of the image might not always be next to each other. If I want to fill this, I need to check all the patches, out of which these two patches are helpful. So Dhaval likes samosa and idli. So his cuisine is Indian. To fill this, I need to think about these two, not the nearest ones. Okay. So every patch looked only at itself or immediate neighbors may not capture the context better. So if you're only looking at patches that shows car wheel, you may not understand whether it's a car wheel or a bike wheel. Okay. So the vision transformers uses attention mechanism to let each patch pay attention to all other patches. How much attention you have to pay to this to this? How much attention you have to pay this to this? How much attention you have to pay this to this? Similarly, this to this, all other patches. Like that, we will completely learn how much attention you have to pay this patch to this patch. That means if I want to understand this patch, how much importance I need to give to this patch. Okay, that means is this helpful to me? This patch is helpful to me to understand about this patch. That is called as attention. Where I need to pay attention, which part I need to pay attention. Okay, so context helps understand each patch better. Next, global information is important for understanding the entire image you have to understand. In that, the role of each word also you need to understand. Some patches may be far away, but still important for the overall meaning of the car. By attending to other means the other patches, the model can figure out which parts of the image are related. So it will come to know that these are the related patches. Tire. So these are related to car. These are related. All these patches are related to mirror, left, right. Everything it will try to understand. By attending other patches, the model can figure out which parts of the image are related to each other, making better classification. Okay, more accurate predictions, more caption generation. So if I want to high level caption generation, I need to understand each and every patch, each and every part of the image I need to consider, where it is related to, which are the similar groups that I need to understand. So in self-attention mechanism, each patch computes its relationship with all other patches. It asks which other patches are relevant for me to understand what I am. So I need to understand the word or the patch. So other patches has to help me. Okay, a patch showing part of the face may pay more attention to other face patches to better understand that it's a face, not just patch of skin. So here also, if this is a car, so it gives higher importance to patches of the car, least importance to this one. So if I want to understand this patch is important. This is also important, but not as much as this. Okay, the model doesn't know beforehand which patches are most important. So it checks all the patches to see which one are related, more relevant patches. The attention mechanism gives each patch a different attention weights. So each patch, you can take any patch and then you have to check the similarity or relevance to all other patches in the image. How important the other patches are to understanding the overall image. Context. This patch wants to understand its role in the image. For that, it has to understand all other patches of the image. So if this has to get understand about where it is, to which part it belongs to, okay? So if this patch is more helpful, like here, it will give more attention, say 99. And say suppose this Honda, maybe the last one. So it may give some 2%. So that is the attention mechanism. Similarly, you can take another. So this patch. And for that patch, again, you have to compute the same set of algorithms. Same importance, where I need to look into, which part will help me to better. Like how Indians will look for Indians in some other place, some other country. Same here. Others also they will talk to, but they will give least attention. Same here. So all other patches here will have more attention and these patches will have less attention. Okay. So that is what. So self-attention is a mechanism that allows the transformer to compute relationship between patches and then will compute the weighted sum of all other patches to decide how much attention it should give to other patches. So a patch of a car's wheel might attend to a patch containing another part of the car, like the body, to understand the context better. Okay, so this is more important. So relationship between patches, how much attention it should give to other patches. So that what is how much attention I need to give. Okay, so that in the sense I can understand my role better. Who will help me to understand my role better, my position better in this car? That patches I will give more attention. Which patches doesn't help me, so I don't pay much attention. Is it clear? That is the importance of attention mechanism. Is it clear? Same thing. X-ray and CT means the tumor related part will get higher attention. Non-tumor will get, areas will get lesser attention. See, there is nothing like type of transformers. The functionality remains same. You can come up with your own transformer architectures. That's it. Okay. The core idea is attention mechanism. So if you take any medical image, suppose say COVID X-ray. So if you take COVID X-ray, so to understand better, okay. So to understand better, which image will help me? Okay, or else you take this. Okay. See here. So each patch, suppose if you're analyzing this patch, okay, then what happens? So suppose if I have a patch here, this patch will give more importance or weightage to this patch, to patches nearby. So all these patches will get higher weightage. And suppose you take this patch, okay. So for this patch, this patch, okay, and this patch, they are not at, it won't pay much attention. Okay, so to understand about this patch may not be helpful. It may be helpful, but maybe 50%. But these patches may helpful 98%. So the tumor detection, whatever may be the issue. Okay, so this is how it will compute the attentions. So similarly, we have to the similar attentions will have more attention weights, and the far away may have lesser. Okay, so that is how the attention will help us to focus. So now let's go to this guy. So this is how each word, okay. So each word, which other parts of the word it has to pay attention. Okay. So see here, how we compute the attention. It's very important. Okay, same formula. It's a formula. You no need to worry. You no need to think about how to compute the attention. It's a blindly you have to apply the formula. Let's see. Okay. Now if you see here, now see. So I have a word thinking and I have a word machines. So what is the first step? What is the first step? Because when you are dealing with English, means a natural language, okay. So you have to work with the embeddings. You have to work with the embeddings. What is it? What is meant by embedding? Tell me. What is meant by embedding? What is meant by embedding? So let's try to take this example in the same J. Elmer. Okay, so how to compute the attentions? So he given two words. So what is the first step he's telling is to compute the attention. So what is the attention? Yes, text representing numbers. It's not a blind text representation. Okay. So when you convert this into a embedding, that embedding will capture the syntactic and the semantic meaning. So that what is the advantage? Tell me. So why you have to compute embedding? Say dimensionality of 512. That means the that numbers like minus 2.1, 6.8, like this, the length equal to 512. The length equal to 512. Similarly, these machines are also equal to 512. Why? So why we have to convert that into numbers? Tell me. And what is the advantage? Can anyone tell me what is the advantage of having that embeddings? Let me take one good example here. See here. So why we have to compute the embeddings? Okay. So see, what is meant by embeddings means this one. So that embedding must represent the syntactic and semantic meaning of that particular word. So that if I try to plot it, that number, see here, I can able to achieve this. Queen and king, the word king, the word queen are very nearby. The queen and computer are very far. And see, women and queen are nearby compared to women and computer. Computer and smartphone are nearer. Computer and king are far. So the meaning it has to represent. That's why we have to convert into embeddings. You should not, it should not be any blind representation. Okay. So when you plot it, it has to represent the natural understanding. So computer and smartphone are nearby. Suppose if there is a mobile phone, it will come here. Okay. Next, baby. So baby may come here. So which is far from king, little bit distance, but very far from mobile phone. So the words has to represent the meaning. That's why we are using the embeddings. Okay. So once we convert these into embeddings, next what we are doing, we are using queries, key and values. So you have to generate query, key and value. So what is meant by query, key and value? QKV. What it means, we just keep aside for a while. First try to understand the mathematical meaning. Okay. So we got query, we got key, we got a value, and we have the corresponding weights. I will show you what is the meaning. Now, once we get the text, the embedding representation, and the QKV, then we have to apply the formula. So once we have the input, we have the embeddings, we have the QKV. Then see dot product Q dot K dot product is 112. Then you have to perform the dot product formula. Dot product divided by square root of some normalization, square root of some number you can divide and then apply the softmax. So this is called as the attention scores. Okay, so this is the formula. Okay. Okay, so now if we go to one more, see here in the attention model. Okay, so this is what happens. Okay, so what attention it is. Okay, so same thing we can just we through RNN we can try to learn. Okay, so in the earlier slides, how the attention is computed. Okay, so how they are computing the attention, but actually how it works, if you see this slides, it will understand. Okay, so initially what happened, if you take any RNN model, which is a sequence to sequence model, taking some set of inputs and they are generating some set of outputs. Okay, now we will just think of why we need attention. How to compute the attention we have seen. Why we need attention. Next, see here, sequence to sequence model. Like this, it can take a word by word, and keep on generating the output. Translation, machine translation, translating into another language. Inside, if you saw same encoder decoder architecture, but here what is happening? See here. So here, see, it is taking all the words, all the input words. It is generating a single context summary, and this context is what we are giving it to decoder, and the decoder takes it and it will keep on translating the generating the output in the destination target language. Only one context. So if you go deeper, see, so here we are taking the words, All the three words are processed by the encoder. The summary of the processing is what given by the context, and based upon the context, the decoder is generating the data. Okay. Now, if you go a bit deeper, if I want to generate, so what is it? Okay, so now see here. My target is to generate the language. I am a student, is what the language I'm expecting. But what is the input here? See, this is the input. So this input, it goes to encoder. Then the output of the encoder goes to decoder, and decoder tries to generate the target language. So what is happening is, first initially what is happening, all the three inputs are taken by the encoder. The resultant of processing of this input by the encoder will be given as a single context vector. So I am passing the single context vector to decoder. Now decoder has to generate. First, it has to generate one word. So to generate first word, where I need to look into? Do I need to focus on JE? Do I need to focus on SUIS? Or do I need to focus on E2D Where I need to focus? I want to generate a second word. You forget about this I am a student. First word, now I have to generate where I need to focus. Second word, I want to generate the translation, the target language. This is a target language, this is a source language. So this, if I want to generate a second word, where I need to look into, that information we need to pass. So if you see here, when we pass a single C, now the three words are taken by the encoder first. This is the first step. And now it generated the context. The context is summary. Summary of this, and this. So I'm passing the summary. With that, decoder will start generating the values. Now the problem is, this is one approach, but if my language contains, say, 100 words, say 1,000 words, and you are giving me a single context vector to generate a first word in the target language, out of these 100 words or out of the 1,000 words, where I need to focus. You got my point? So now they improvised it. So what they did is, okay, so rather sending a single context vector, they try to generate 3 context vectors. Okay, so that is called as the attention mechanism. So earlier what is happening, the single context vector people used to get only one context vector. Okay, see, I am getting only one context vector. The processing of these 4 words will result into the context word, and this context word is what I am using further. So I am using the context word to generate the next word, and the same context I am using to generate the second word also, third word also. Okay, so see here. So if you see here, this guy generated the context vector. So here, okay, so we got a context vector for all the 3 like this. So now if I go here into my this one, so this context contains the information about all the 3. So now if I want to generate the first output, where I need to focus? Do I need to focus on this? Do I need to focus on this? This is not given by the context. So context is a common single vector. I mean, it's like a specific generalized vector, which summarizes the information from these inputs. But if I want to give an output, first output, and if I want to give a last output, the focus must be different. So if I want to give the first output, I need to focus on the first inputs. If I want to give the last output, I should not focus on the first. Okay, so that's why what they did is the approach they modified to attention. So what they did is, see here, they bring in the attention mechanism. So based upon the attention mechanism, what will happen is every time a new context is getting generated. See here, C1. So I am doing some operation. I will explain this. So I am doing certain operation, same formula. Okay, some formula I'm applying, I'm getting the output, and that output is what? Context, new context. If I want to do another input, see another, I'm generating another context. So next, like this, I'm making the context dynamic. That is called as attention mechanism. To generate S2, which word I need to give the importance. To generate at S1, where I need to focus. Learning this is called as attention. Got it? So now you have to correlate between the car example, English example, and this example, and this Almar also, J Almar, this applet. So initially, what is happening when I want to perform any translation tasks, I am getting a summary of the input through an encoder, and that is a context. That context cannot give me any information about the all other words. It's a generalized version. So if I use that context, my translation may be inefficient. But what I want, if I want to do print the first word, I need to look into which parts of the input. I need to learn that. Next, if I want to generate the second output, now where I need to look that. So that is called as the attention mechanism. So whenever the attention came into picture, where I need to focus to generate this one, where I need to give the attention. To generate this one, where I need to give the attention. So to understand what is this patch, the car patch. Okay, so so now if I talk to in that car language, okay, so so if I talk to in terms of car language, then what happens? So this is the input. Now I need to understand what is the context. Okay, so now I want to understand this context. So if I want to understand about this, okay, so if I want to understand about this particular patch, where I need to look into, do I need to look into here? Okay, so where I need to look into, do I need to look into here, here, here? So that is what the context is. Okay, so to understand about this particular patch, you have to look into these words, this tire, and some parts of the car. Same here. So if I want to generate an output, okay, for this output, which part of the input I need to look into? So a single context may not be sufficient, because with a single context, here also same context if you use, it may mislead. So what I need is, I need different context. So what are those different contexts? Yeah, I think see here. Now what is the improvement? The improvement is like this. Okay. So what the improvement they did? So first word it will go, process it, get the context. And then that context, hidden 2. And then that context, third hidden. Now what we are doing is, okay, final one we are sending. That is one case. But now you see this advanced case. This is the attention case, where if you see, 1 second. So hidden state 1, hidden state 2, hidden state 3, No, this is also world case. See, now attention mechanism. Let's pay attention. So in this attention, what happens? See here. First, I'm submitting, I got hidden state 1. Then I second word went, I got hidden state 2. Third I went, I got hidden state 3, 2, 1. All three I'm sending. Based upon that, now see attention decoder. So now you see here, this is the attention mechanism. So what it says, this is the case. So if you see any other technique, so what we are doing is, we are not sending full summary. So somehow, in state 3, first what is happening? In the first case, I am sending only the last one. See, this over, I got the last one, and that's what I'm sending. In next improvement, what they did is, see here, like this. So hidden state 1, we got submitting hidden state 3, and this hidden state 3, I send it to decoder. That is also not sufficient. Now what I did is first input I got, okay. So if you see carefully, first input I'm going to submit. It processed the encoder. It given me the summary or the context, which we are calling as a hidden state. And then it taken the second word, it taken the hidden state also, and then it generated the hidden state 2. Next, it taken the third word, and then hidden state 2 as an input, it given me the hidden state 3. Now, all the summary I'm passing as an input to the attention, the decoder. So now what decoder will do is, decoder has to decide, if I want to generate the first output, where I need to look into. Do I need to look into here, here, or here? So now see, okay, next, based upon this, internally he did the logic that maybe first time he given importance to this, second for this he may give importance to this, and third he may give importance to this. So that is called as attention mechanism. Clear? Got it? Any doubt? So the ultimate aim is, yes. Okay. So to perform any task like caption generation, translation, etc., what happened at the decoder level, all this will happen. At encoder level, what happened? That I need to understand. Okay. So now you see, once I get those from the encoding stage, okay. So see here, attention mechanism, I got 3 encoding stage. See here, same. I got 3, right? Now where I need to focus, how I can compute the, see here, now I will show you. Now among, I have these 3. Now when I want to answer first output, how to compute the attention. If I want to give an output for this, again, my attention has to change. It should not be the same. Why? Because my second input may not be dependent upon the first hidden state. That means the first source. Correct? So if I want to answer third, I may look into 2 and 3. If I want to answer 4, I may look into 3 and 4, but not first. So now if you see, we got like this. So 3 hidden values, which is equal to these values I got. Next, what I will do, see. Suppose, assume that score each hidden state. Now attention waits for decoder step 4. So now see, this is the decoder step 4. This is the decoder step. Okay. Now decoder step I need to perform. How much importance I need to give to this? See, score each hidden state. So if I want to answer the output, if I want to generate the output here, now I need to give the output. So this output, see, attention weights, now these are the outputs. So 13 will get, the first hidden one will get more weightage, and these two will get lesser weightage and equal weightage. And then how we got this, I will explain in a time. But we got this score. So these are the attention score. So to generate the first output, okay, the first hidden vector plays a major role. That's why its importance or attention is very high. I applied some formula. So, and when I do the softmax, I got 96%. So 96% I will depend upon H1, 0.02 on H2, 0.02 on H3 to generate the first output. And see, multiply each vector by its softmax score. Each output multiplied with each element of these vectors. And now see, this is thick. This is almost very, very light. When we multiply 0.02 with these numbers, automatically it will reduce. And now if you see, if we add all those, this should be the context vector for decoder. This is my context vector. This information you have to use. Okay. So now if you see here, when we get the hidden values H1, H2, H3, okay, so we have to perform the, when we get the attentions, okay, see here. So we have to compute the context vector. Okay, so see here, we will, first time what happens, you see, attention, I want to compute the attention. So see here, first time, this one, like this. First time when I compute, this will get higher weightage and these two will get lesser weightage. That is what I can show it here. Higher color, very least color. And see, okay, so with this, see, this is what the context vector. Here I computed the context vector. So this is my context vector and this is my input. Okay, so both I will add, this will give the output. So this output, for this output, I need to give more importance to this hidden state. That means I need to give higher importance to JI, that word, that JE. So JE is the word I need to give more importance. Now see, next time. Next, the output forms as an input to this node. And now see the hidden state, the hidden value, I have taken H5. And now the context, again, I need to compute the attention. So to generate an output, at this decoder stage, which inputs I need to give more importance. So that summary I have with H1, H2, H3. And now when I apply the technique, see here, see, now here I have to give more importance. This is more better color. First time, this is more better color. So that means second input will have more weightage. And then if I multiply the weights with the values, I am getting that these are the weights and these are the this one, weights and the numbers. When we multiply, we are getting this context vector. So this context vector forms appended together the hidden state, the input, the hidden state. That means what we are getting from decoder, the output of the decoder plus the context, both I combined to get a new output. Okay, so to compute YAM, I need to focus on the second one. What is that second one? That is Swiss. Okay, next word, like the same. This will form as a input. AM will form, they didn't given. So AM will form as a input. Okay, so J, Swiss, idiot. When, see here, if I want to generate the first output, I need to give more importance to hidden state 1. So when I need to generate AM, I need to give more importance to hidden state 2. Okay, then if I want to generate A, I need to give near means maybe 48, 47, 3, remaining 3 here. And to generate the fourth one, I need to give more importance to IIITDMJ. Hidden 3 is generated from IIITDMJ. Hidden state 2 is representing the Swiss. Hidden state 1 is representing the JE. So to translate, to generate the first output, I need to focus on here. To generate second output, I need to focus on here. To generate third output, so these two will play a major role, 2 and 3. And for the last one, this will play a major role. So this is what the attention mechanism for each output, which input you need to look into, like this. So L means the accord, higher color, agreement. So that is how the Is it clear now? Anyone? Any doubts? Yes. Is it clear? If clear, please ping clear. Please type. Swapnil Pagadi. Okay. Others? Okay. So, what is the ultimate aim of attention? Can anyone tell me in single line? What is the ultimate aim of attention? If you are not responding, means you are sleeping. So when I ask, please respond. Okay. So now why we need attention? Now tell me why we need attention. Can anyone summarize in 2 lines or 1 line? Type. Very good. Very good, Rajshekar. Rajesh Kumar. Very good. Further, what the attention will solve? Which problem attention will solve? Dini Thomas, correct. Kaushik, correct. Yes. Putijan, allow the model to focus on the most relevant parts of the input when making prediction. Okay. So in any task, either the classification, I want some task. I need to solve some task. For that task, I have an input. So where I need to focus. If it's suppose if it is a translation, I need to generate the words. Maybe the first word. If I want to generate the first word, which words in the source language, which words in the input language will help me? That is what I need to learn. And I should not use the same context. Second word, where I need to focus on. Third word, where I need to focus on. So for every output, which part of the input will help me to make it better? That is called as attention. Hope is it clear? Okay. So if you follow the same context, see that's what. If you're writing a maths exam, you will take maths book. If you're writing a C exam, you will take C book. So for every exam, you need a specific book, specific context. For maths, you never take C book. For C exam, you never take maths. If so, your output will fail. Means your exam will fail. So that is called as attention. For a task in hand where you need to focus, which book to take for which exam, that is called as attention mechanism, simply. And how to do that? Mathematical operations. Okay. So, okay. So I think mathematics, as he explained. So Q query, some operations are there. See here, multi-head, some operations. Let me check. Let me check because if I show visualization, it will be useful to you. Okay. So this you understood. Clearly you understood. Now, so what is the drawbacks? Everything we studied. Okay. Now let's again go back to the transformer. So this and all we studied, self-attention, all those things. Okay. Now see, that's what. So the input, from the input, what is the ultimate aim? I need to get the numbers. Okay. So if you see here, what is the ultimate aim of attention? Ultimate aim of attention is I need to get the numbers. Numbers means, can anyone tell me? Let me open, let me take this and I'll keep this here as it is. One. Okay. So So what we need is attention mechanism. This is core, okay? This is what more important. Yes. So this is what important. Okay. Now you see if you go to this transformer, how to compute that? Okay. It's a formula. What is the formula? So for a, let me open my paper also. I will show you the code, how we will learn those values. Okay, so if you see here, this is the how the attention scores are computed. Okay, so this is how you are giving the inputs. This is the input. Okay, but main thing, if you see in this the input, okay, that input you are giving it to some operations you are performing, attention layer, etc. So here I will show you. So this is the input. This is the input. The input goes to Q, P, and value. So the input, the same input, you are giving it to three vectors, means three neural networks, query, key, and value. Now what happens? The ultimate aim is when we submit an input, okay, so we need to transform them. The transformation, okay. So that is when we submit this input to the dense network, neural network, that neural network will give an output that is called as query. So same here, you will also experience the query. The input first we will get the query. Next, for the same input, we will give it to one neural network. That neural network is called as a key. The input we give it to another neural network is called as a V. Then what happens? This neural network will process the input. It will generate the output called as query. And key neural network will generate a output from the input called as key. Same value neural network will generate a vector value. So this is blind formula. You don't need to worry anything. Out of which the key must be transposed. So 100 comma 256 it will become 256 comma 100, and query remains as it is. Both you have to match multiply. Same here also. So Q, K, V you will get, out of which Q and K you will multiply. Same here, Q and key you will multiply. Then you will do some scaling operation, some divided by some number operation. Okay, so after multiplication, you are performing some division operation, some scaling. If I do that, you will get this number. And then you apply the softmax operation. You apply softmax operation, then you will get the 0.88. Same here, query into key like this. Okay, multiple keys. What is this? You are finding. Okay, so see here. So out of you are finding attentions where I need to look into. So see here. So this, do I need to match with uh, key Q and Q key? So which is closer to me? Okay. So for this input, I got Q K. Another input. Okay. Q, K, V, same thing. So I will compute which is the query, which is nearer by. So thinking is nearer to this or machine is nearer to this, which one I need to compute. So I will perform the dot product. Okay, so 112 higher dot product, higher score. When I normalize, and then I will take the softmax, so I will get 0.88. So thinking, I have to map it to Q1. So how to map? Same here. To get an output, here, which output from the encoder I need to focus. Okay, so this is the formula. You have to submit the input to Q vector, and then you will get a Q values, key network, you will get key values, match multiply it, scale it, find the softmax, and then you multiply with value, match multiplication with value, see here. Next, you will multiply with the V value. Okay. So finally, what happened? The input, from this input, I got Z1. And for this input, I got Z2. Okay. So that is how you will compute the vectors. And those vectors will go to the next layer. Clear? So this is a blind formula. Based upon that, you will get the attentions. Clear? Any doubts? So if you see here, the each input, we have to get, see, ultimately what happened, we have to get these values. These values. Just now we have seen, right? While computing H1, this one, these are the inputs. And then you see, we have to get these scores, these values. How to get these scores? And once you get these scores, then you will perform the softmax, etc., etc. But how to get these scores? So that is what happens here. So the input, you have to map it to one, give as input to the network layer. That network is called as a Q, and then that is given as a input to the if you give it to this network, it will give you the output. That is called as a query matrix value. Same to key, you have to give as an input. You will get the key matrix. You have to transpose and you have to perform the matrix multiplication. Same algorithm here. So first you have to perform the Q1 dot K1, and then you have to normalize. You have to compute the softmax. Okay. So this is the formula. Same formula for every input. You have to go through that. You have to feed it to the neural network. That neural network will give you some set of weights, which you call it as a weight matrix. Query, same key, transpose it, and then perform the match multiplication, perform scaling, softmax. Then you will get the values. So this is how you will get the attention output. Same they explained here. So once you know the softmax, then you can multiply those softmax into the value which you submitted, this one values, you will get the sum. That means the output. Okay, so see here. You have to multiply and then you have to add, you will get the context vector. So higher importance, where I need to give the importance. So inputs, you are multiply, see inputs, you are multiplied by the score of hidden state. These scores you are getting here, this one. Okay. So finally, you will get the attention weights. Okay. Is it clear? This is the formula. From each input, you have to get the output, attention, values of attention. Clear? Any doubts? Vinny Thomas. Any doubts? So the ultimate aim is, if you see here, the ultimate aim is for each output, if I want to, for each output I'm going to generate, you have to assign the numbers. If you want to generate this output, you have to assign the importance to these numbers. If you want to generate the output, third output, where how much importance you have to assign to these three inputs. That is attention. Okay. So if I have these three, how I can pay the attention? That attention is what score for each hidden state. That means the attention weights. So attention weights is a formula. So based upon the attention weights, we will perform. So that I will show you here. I also have a slide. So see here, what is the formula? Okay. So this is the input and output. That is what I explained here. Same context never help us. So you need to get multiple context. Individual context you need to get. Okay. So like this, somewhere I have seen. See here. Context C1, context C1, next context C2. So how to generate? You see the slide. Okay. So first see here how we are going to see. This as the input we have. Okay. So we are eating bread is the input. But that input you are transforming, you are giving it to some embeddings, and you will get the embeddings out of it. The input, you will get the embeddings. So now you see, this is the formula. Okay. Uh, that's it, right? Here. Okay. So what we are doing, see, we are computing the E value. Okay. So what you are doing, ST minus 1, H1. See, H1, HI is the hidden value. So hidden value you will substitute. And previous, the input value, state value, ST minus 1, and you are performing some operation, you are getting ET values. Okay. So from ET value, see, this is the S naught value. So S naught, see here. Once you get ETI is the alignment score between ST minus 1 and HI. So which hidden state? I have multiple hidden state. Now I need to generate the output. To generate the output here, which hidden state I need to compute? That is the case. Got it? Okay. So at S1, I want to generate an output. To generate an output at S1, which hidden state output I need to consider? Okay. So that is what we are computing here. Where it is? Okay. So ST minus 1 is the state where I want to generate the output from the decoder. For that, how much importance I need to give to H1? Like I varies. That means to H1, to H2, to H3, to H4. So all the hidden states I will compute. What I will compute? The importance, the alignment score. Who will give me? This is a neural network. So the neural network, there will be a neural network. Okay. So the previous state, if wherever I want to generate an output, the previous state and the hidden state values I will take, and then I will compute the attainment scores. So to generate an output here, what is the importance I need to give to this is called as E11. It is called as E12, E13, E14. That means the first output, if you want to generate, how much importance you have to give. I'm not getting this. Juhi Faridi. When we are generating context vectors from the encoder, when we pass on these to the decoder, okay, it acts as a hidden state for decoder. No. Decoders will never change the context vector. Will never change the context vector. What they will do is, see here, when I want to generate an output, okay, the problem is I have a single context vector. From all these hidden vectors, I got one context vector and I got some S0 state, initial decoder state. S0 is called as initial decoder state and C is the context vector. This context vector and this initial decoder state I am giving as an input to S1. So here what happens, it will take some start, decoder's output will start. So it will take Y0, all these three. Okay, so it will take YT minus 1 and it will take ST minus 1. It will take the context vector and try to generate the output. So C is common. It never take. It will perform some operation. Oh, okay. Got it? So initially, so here by here encoding is over. And here the decoding is going to start. So these are the initializers, decoder state, decoder context, and start. So at each state, it will take these three values, will do some operation, and it will give the output. Okay. So if you see here, the output. What is the output here? So ST. So ST equal to, so YT minus 1. Okay, YT minus 1 means this one, and ST minus 1 this one, and C. And okay, so we are giving it to the some operation and then to do the ST. So the context is the problem here. And then what we did is the same context we are feeding in. That's why there is no index for the context. That is a problem. Which context? For this output, same context never help. So for each step, I want to change the context. So that is what happened in this work. So what we are doing initially, for first output, I'm generating C1. So see here, so what we are doing, I'm taking the input and that input I converted into embeddings. Embeddings, I given it to H1. And then see H1, then I'm computing E1. So how I'm computing E1? Okay, so see here, ST minus 1, H1. So my score, my H1 score and this ST minus 1 initialized score, both I will take, I will compute the E11. And then what I will do, I will apply the softmax, I will get the attention. That attention, I am giving it to as a context 1. So S1 will take the context and Y0. Clear? So for my input, okay, so I did X1 is embedding. That embedding went to this encoder. This is the encoder. So for one input, I got H1. For another input, I got H2. For another input, I got H3. For another input, I got H4. Now what I did, I am taking this, I need to compute the alignment score. Then attention, what is alignment score? Alignment score equal to, see here, this E1 will take C, the state, the previous state, and all the hidden states. So I need to compute E1, comma 0, E1, comma 1, where 0, this indicates, okay, so sorry, it is 1, 2, E1, comma 3, and E1, comma 4. So 4 values I need to compute. How I will compute? I will take the S0. So to generate S1, for S1, it needs the context vector. Anyhow, the output, the Y0 will be there. Y0 we don't focus. So we need to get context. So to generate S1, S0. S0 is some random values. So each hidden value, and each S0 value, both I will pass on to some function. and that function will give me the alignment score. Okay. Next, those alignment scores, I will apply the softmax. Then I will get the attention scores. Then those attention scores, okay, I will add those attention scores, and that is what my context vector. Not visible. Why? It is in sharing only. It is share only. Now are you able to see? Now are you able to see? Okay. So I need context 1 for S1, and I need context 2 for S2. This is the decoder size. This is the encoder size. So this is the initial starting point of the decoder. So rather using only one context, okay, common context for all the states of the decoder, what we are doing, at every time we are generating the output. We are generating C1, C1, C2, C3 for each output. How we are getting this context vector? See here. So this is my input. That input is converted into embeddings. So embeddings, I given it to my hidden state. Some processing I did through encoder. Some logic I applied. Okay. Okay. So some logic I applied in the encoder. I got hidden state. Similarly for second hidden state. So 4 hidden states are available to me. Now what I will do? Okay, see here. For each state, suppose I want to generate with the context vector. That means which importance I need to give to these hidden vectors. So for S1, I need to give. So what is the formula I have? This is the formula. What is that? You have to generate alignment score. From that, the attention score. What is my alignment score? You are multiplying or some operation you are performing between. Suppose for S1, if you want to generate, it will be S0, comma, H1. Similarly, S0, comma, H2. Similarly, S0, comma, H3. Like this, how many hidden states are there? Those many ETI values you will compute. ET1, ET2, ET3, ET4. And all those values you will try to compute softmax. You will get the attention values. And those attention values, like you will take the addition, like suppose you will multiply. Suppose 90% if you want to do, so 90 into hidden one. Next 3%, so 3 into this one. Same, 2 into this one. Last 1 into this one. And those vector is called as context vector. So this is context vector. And already here you will generate, and then y1 you give as an input here. Then dynamically again you will compute this S2, this S1 you will pass as an input to the E1. Then again, S1, how it is related to H1, H2, H3, H4, you will compute. And that is your context vector. Okay. So if you want to generate S2, S1 you will consider, and how it is related to H1. So you will apply the formula, this formula. Next for S3, it will become S2. So S2 comma H1, S2 comma H. Like this, you will compute which hidden values helpful for a particular output. Like this. New context vectors we keep on creating. Okay. Any doubts? Is it clear? For every prediction, you are using a context vector. That context vector tells us to generate current output, which parts of the input you have to give importance. That importance is attention. That is equal to context vector. Obviously, yes, very good. So as the input increases, every time you have to generate the context vector. So that increases the computation times. Yes, obviously it will increase. That's why the latest transformer based models are very high, very large in number. So let me show you the code. Okay. So let anything, anything. So embedding by 12, 1024, same problem. If you use 1024, the embedding size will be more. You need to be careful. Okay. So that is you have to hit and trial. You have to do experiments. So which size will is giving you the best accuracy, that size you have to set. Okay. So let's show you the code. It's simple. Okay. So if you understand, see, this is the code which I'm running. Okay. So TensorFlow based application. So I am using the Inception V3 model. Any model you can take. So now I have taken the data set like Coco data set for captioned images. So I have images and a JSON file with the captions. So what I did is images and corresponding caption, I created one list. Okay. Then see here, I just checked loading the images. So I converted the into data set. So tokenizing C, number of words. Okay. So which are all the words I need to take? Okay. Captions, because captions I need to convert that into embeddings, right? So tokenizer will tokenize it and start pad equal to 0. Starting, I have to set some value. Okay. So that is the case, train and split. And then what I'm doing is, see here, attention mechanism I need to compute. I have weight W1 vector, Q, K, V vectors. Okay, so this is the main part of the attention mechanism. So see here, W1 features plus W features, I'm computing the scores. Attention equal to softmax. You have to apply same thing. Whatever I explained here, whatever I am explaining, the input going to the weight vectors, mathematical scaling, softmax, same I am doing here also. So I am that input I have taken. So weight vectors plus this weight vectors, I am applying the tan h. Okay, softmax. So this is the softmax. I am getting this multiplication. Okay, so I am doing it here. Now I got the context vector and the attention weights. This is regular encoder and decoder network. Okay. So I'm actually, it is taking time. It is running. I will share the code. You can try to run. It's a simple only. This is not required actually. Once it is trained, what you can do is you can take any image. You can take any image, extract the features. And what you can do is, see here, you can get the attention. Attentions for any image you can upload, and then you can call this function. Okay, evaluate image path, and then you can try the plot attention map. Okay, so you can able to get the attentions and the description. Okay, so this is the main part of the training. This one, attention weights, softmax, V vector, W1 and W2. See, W1, see, what you are doing, see, you are adding self dot this, self dot this one. Okay, that is one kind of attention mechanism. What are the features? These are the features. So features will go to this, you will learn some weights. Feature go to this, it will learn some weights. Those weights are W1 and W2. That's what we are calling it as a W1 of the features, W2 of the features. And that here I'm using mat multiplication, but you can also add them. That is called as Behnow. See here, you can add those. That is called as Behnow attention. Okay. And text vector and attribute. Every time you have to call this. Any doubts? Yes. See, embedding means no, there is no textual embedding. Textual data you are converting into embedding. That embedding is a pi hand tall size numbers, float numbers. How many weights means it depends upon size of the input. Your size, if input size is high, you have to give more weights. Model will learn. Through training, it will learn. Any doubts? Ah, different methods of attention means Behadinov attention is there. One what we use dot product attention. Two to 3 to 4 attention mechanisms are there. Widely used is Behadinov and dot product. This notebook I will share. Yes, the input. My name is Mega. The input numbers is see here. If that is the case, it will be like this. So like this. My name. Okay. So like this, you have to give it to the network. And for each word, we will get the embeddings. Weight we cannot say. It learns. With a single word, it won't learn. Multiple set of words we have to train, and then model will learn. We cannot say for single word, we cannot say the weights. Okay, if no doubts, we can stop it here. See, you no need to code from scratch. What is the important step? How they are implementing, if you know, see, in this entire code, this is important. This is where you have to focus. What is that? This one. That's it. How they are computing. What is the input and how they are computing. If you know this, enough. You no need to by heart the code. You need to understand. That's it. Okay, so if no doubts, we can stop it here. Okay, thank you. Thank you all.
Thank you so much, sir, for joining us today.
Thank you.
It has been really a journey since morning where the students are studying this only. This morning also theoretical session was there and that it continued a bit. So thank you so much. Thank you very
I
much.
shown the code also.
Yes, yes, yes,
I
ma'am.
will share the code so that the people you just run it. No need to by heart the code. You just understand what is happening and then you just play with the inputs. That's it.
Sure, sir. Sure, sir.
Okay. Thank you. Thanks all.
Okay. Thank you so much, sir. Everyone can leave the meeting. The session is over now.